Memory mapped input and output, or memory mapped IO. So as it turns out, an embedded system needs to communicate with the surrounding physical world. For example, displaying some patterns on an LED, or reading some switches, or some sensors, or even communicating with the other SoCs. And in order for it to do so, it needs some I/O modules. And I/O modules are generally controlled and by writing and reading into some sort of internal register. So in here, what I'm showing you is there's a bunch of modules in here. We're going to see the details of each one of these modules later. But these modules can be basically our way for our embedded system to actually communicate with the rest of the world. And in order for us to do so, we need to figure out the internal registers of each one of these modules. So these internal registers can be used for issuing command, or reading the status of that module, or even reading the data that it read. For example, if you're talking about an LED, maybe a register inside will actually contain the pattern that needs to be displayed on the LED. So in order for us to display a certain pattern on the LED, just change that value of that register and it will change it. So how do we actually change that value? Well, we need a processor. So the processor in here will actually have to access this particular register and change it. And as it turns out, there's a couple of ways to access these registers. One is called the standard method, and the other one is a memory mapped IO. And the difference between them is how does the processor see that particular IO. So we will be adopting the memory mapped IO subsystem, or the memory mapped IO scheme, and this is why we call it the memory mapped IO subsystem. And in that particular scheme, the processor does not know the difference between its memory and the IO. So in here, what I'm showing you is I'm showing you some address space or memory map. I use these terms interchangeably. And this particular address space, what it shows me is that there's RAM located in here, and that's its base address. There's some sort of a timer core in here. There's a UART core in here. And of course, I'm just going to not use this particular part of the memory space. Okay, how important is this? Well, it's extremely important because in this method, what the processor does is the following. If it needs to read into a certain location in RAM, it can just basically figure out its address, read or write from it. What about the I/O? Let's assume for a timer, if I want to figure out what's the time that passed. Well, the processor just goes and read the value of that timer, and it reads it as if it's reading its own internal memory. So this is why it's called memory mapped IO, because from a processor perspective, I don't know which one is IO, which one is memory. Functionally, they're extremely different, but the processor doesn't know that function difference. All it knows is I'm reading and writing. And this is extremely powerful because that means the processor can just issue the same read and write command, whether for RAM or whether for the IOs. Okay, so how does a processor know how to communicate with a specific register? Well, here's how it does it. So we have a timer core, and let's assume that the processor needs to go to its register number 1 and read it or write into it for some reason. It needs to communicate with it. What it does the following. It goes and say, okay, what's the base address of this? And the base address is actually where did you put that in the memory map. So in here, the RAM is basically located at location 0. If you want to communicate with row number 10, all you have to do is just add 10 to that base address. The same goes with the I/O. What it does is the processor needs to know where is it located, basically what's its very first address. And in this particular case, it just happened to be at location 0100. And we know that that particular processor needs to communicate with the register 1, so all it needs to know, like, what's the offset of that particular register, and it just turned out to be 1, okay? So the processor adds these two, and it knows that this particular address in here, if I communicate with this particular address, I'll be writing in that particular memory location. For it, it's a memory location. For us as designers, we know that we're communicating with an I/O core, and maybe this particular register is just basically outputting something to the rest of the world, or actually inputting something from the rest of the world. Okay, so that's great. So now we know what type of schema we're using to actually communicate with I/O cores. So as it turns out, the processor that we're dealing with is a 32-bit processor, which means that it deals with 32-bit words, and most likely it will be 32-bit address space as well, or address, the address pins on its bus. So we're going to focus now on the word, and we'll get back to the address later. And the reason why I want to focus on the word, because as it turns out, memory, in terms of memory, we can actually store words in a couple of different ways, but the major two ways that I'm going to think about it is the following. in here, I'm showing you an example of two words being stored. So I'm showing you an example of a word in here. This is the least significant bit. It's actually location 0, and most significant bit, which is location 31. So in here, what I do is I have a couple of words, and each one of them is 32-bit. So what I did is I'm going to have a memory. Basically, it might have many, many rows, thousands of them, and each one of these rows contain a word. And a word could be 64, could be 32. In our case, it's 32. So this is an easy way to actually deal with the memory. But for some reason, for an older reason, basically, it's a historic reason, memory happened to be arranged in bytes. Basically, each row in that memory can be dealt with separately. So I can address a byte as opposed to addressing a word. This is generally speaking why whenever you buy something, it tells you, well, it's 2 kilobytes or 3 megabytes or something like that. Like you don't see it called the 2 kilo word or something like that. And especially like our processors nowadays are 64-bit or 32-bit. We still deal with 8 bits or 1 byte basically. Okay, so that means that this particular word have to be split into 4 different bytes, because 32 divided by 8 bits is actually 4, and that means I need 4 bytes. Okay, so what we need to do is we need to figure out these bytes. So these colors in here show me an example of the same exact 2 words in here arranged in a memory, or in a memory that is basically arranged in rows of bytes in here. I'm showing you in here one method of doing this. So what I did is I took this least significant byte and I put it in the first address, or the smaller address. And then I took the next one and I put it in here, and then I took the next one and so forth. So there's another way. Instead of taking the least significant byte in here, what we can do is we can actually take that particular one, which is the most significant byte, and start in here. So the difference between the two is actually what we call a little endian or a big endian. The method I'm showing you here is what we call little endian, and this is the convention we're going to be using. Some processors use little endians, other processors use big endians. We're just going to be using the little endian. Okay, so that's great. So that means that each one of these words that we're going to be dealing with to communicate with the IOs, or the memory actually, is going to be arranged in 4 different rows. And if I keep this memory this way, and I can basically put any word in any location in memory, or any location I want to, but that creates some challenges. And let me show you what type of challenges we might get. So in here, I'm showing you an example where I'm storing a couple of words, okay? And as it turns out, like if there's some sort of an error in my address, because the way I'm reading my address, and I issued an address, hey, this is the first byte, that means I will be reading half of one word and another half of the other words, and I'll be completely assembling a wrong word in here. So in order to avoid this, we do something we call a memory alignment. And a memory alignment tells me, okay, well, you have a 32-bit in here. In order for us to actually arrange it, what we need to do is we need to, if we divide it by 8, because I'm arranging it in rows of 8 bits, we know that we need 4. So let's make it in a location that is divisible by 4, or basically a multiple of 4. So let's always assign the first byte we need in a place that is actually divisible by 4. So in short, what this tells me is the following. It tells me, okay, let's assume that I want to store this particular word in here. That's the whole word that is 32-bit. And I want to just basically store it 1 byte at a time. Okay, so well, taking a look at the address, you're going to see the following. If you arrange it in locations that are divisible or multiples of 4, you're going to see that the least 2 significant bits are going to be 0, 0, then it comes 0, 1, and then 2, and then 3. Whatever the address in here, I don't care at this point, because taking a look at another word in here and seeing it stored, you're going to see that its first byte is always located at location 0. This is why we call it alignment. So whenever we issue an address read or an address write, I need to make sure that the first byte I'm actually looking at is actually located at 0, 0. And if that's the case, I'm guaranteed that I'm reading the correct word. I'm not actually reading a word or half a word from each, or sometimes it's even worse. I might get like 1 byte from one and 3 bytes from the other, and so forth. So the memory this way is aligned. And this type of alignment actually creates some sort of a confusion whenever you're programming. So you need to distinguish between a couple of things. Well, if you have 32-bit for address, and that means you have a 32-bit byte addressable in this particular situation that we're dealing with. Okay, so whenever I say I have 32-bit for the address, you have to tell me what type of address do you have. Do you have a byte address or a word address in here? So the difference is it's just these 2 bits in here in this particular situation. So whenever I say 32-bit, I meant 32-bit byte address. If I want to deal with the word address with the same address space or the same addresses, you can just basically ignore these least significant bits, because you know you don't care about them, because you're not going to access half a word or part of a word or whatnot. We're going to just read the whole word together, and you can tell me, well, I just need 30-bit for the whole word address, okay, because the memory is aligned. So whenever you see an address, just think whether it's byte addressable or word addressable. The I/O cores, their register internally are not the same as the RAM. Yes, these registers are 32-bit, and of course they're going to be arranged. You're going to see that we're going to split them into 4, and we're going to access them as 1 byte at a time, but we're going to read all 4 bytes together. This is okay, this is because the memory is aligned. But what's more important is in I/O, the data that it contains is not homogeneous. It's not like the RAM. In the RAM, it's basically the same. I'm just reading data. They're a bunch of numbers or characters or whatever you want to deal with that data. But in here, these registers have a meaning. So whenever we're going to deal with an I/O, we're going to deal with something we call an I/O register map. So an I/O register map, the one I'm showing you in here, is actually for the timer core. And a timer, as we probably know from digital logic, is just basically a counter. So if you look at a counter or a timer, all you need to know is it's the number it reached. So you're going to see that the timer we're going to be using is actually a 64-bit counter, or frankly speaking, I don't remember it exactly, but I think it's 32 and then half of the other byte. But anyway, for now, what we need to do is we need to know that we also need a register map to figure out what is the internal components of this, or what are the internal registers for that timer. So as it turns out that I have at offset 0, this is here the offset, I have the lower word of the counter, and in offset 1 I have the upper word of the counter. And in a counter, or basically the timer, I'm not going to write into it, I'm just going to read it, and that's what you're going to see the type of access we have. As opposed to RAM, any location is readable and writable. In an I/O register map, you might want to know whether it's readable or writable. It's actually important. You shouldn't be writing into a timer. You should just read from it. And the last one in here, you're going to see that this is actually writable, and these are the commands. So these one are data registers. Here are command register. One tell it to go for the timer, the other one will clear it. So when go is 1, it's running. When go is 0, it's paused. And clear just basically zeroes out these ones in here. So in short, what you need to know is you need to know that we have an address map for the whole processor, and each one of the cores, each one of them will also have its own internal maps, so that we know the functionality of this particular core. Different cores will have different maps, because the meaning of these maps are different. And in here we have something we call mnemonics, and it tells me what does that offset mean do. Like each I/O will have completely different things because they're not necessarily RAM.